Audio. Cool. Right up there. Good. Cool. All right. Sorry about that, gang. Let's Nope. What did I do? Is this on Chrome?
No. Not Chrome.
Oh.
Which Chrome is it on is a good question.
Eeny, meeny, miny, mo. Okay. There we go. All right. Cool. All right. Cool. Sorry about that, gang. We can get started here. My name is Sam Curry. I'm the CEO of Heyo Computer. Previously, I led infrastructure at Flatfile and then Obvious AI. Before that, I was VP at a company called Simuant that was here in Denver as well. So, been kind of around the block as far as it concerns like how we deploy applications in a modern environment. Isolation systems have been kind of paramount to that even before the agentic era, but they kind of took a special prominence here in the last several years. This is the presentation that we're going to have today. We're going to start out just by talking about the use cases for isolation systems, why we even want these things in the first place. We're going to quickly define some definitions as far as isolation goes. And then before we get into the mechanics of it, we're going to talk about a brief history of isolation systems in computer science. I find this really helps frame where we're at in 2026 and kind of the solutions that are required, especially when we start talking about agents, which I think most people are probably interested in. And then we're going to get into the actual mechanics here. Namespaces, which I'm using for a group of technologies for isolation systems, containers, and then virtual machines. And then if anybody's interested in this presentation, we have a lot of resources that we have as well. All right, so why do we want to use isolation systems? We're going to split this up into two sections. So pre-agents, so we think maybe like 2022 and older, and then we'll go into the post-agent era where we are now. All right, so pre-agents, there's a number of different reasons why we're going to use isolation systems. Cloud infrastructure being a big one. If you've ever used Amazon's EC2 service, this is a virtual machine. They use something called the Nitro hypervisor. And then Google and Azure use something called libvirt, but they're all virtual machines. So they have their hardware, a hypervisor layer, and then the product that they give you is going to be a VM. This allows density in terms of multi-user systems. Other use cases here, running a guest operating system on your computer. So if you want to use Mac OS, but then operate on Linux, that's one use case. Scalability, Kubernetes, and then probably the real reason containers are so popular right now is because as an isolation system, it actually makes it really easy to package up applications and distribute them. So we'll talk about Docker a little bit later when that came on the scene and containers kind of just exploded. But there's a bunch of different reasons for actually using isolation here. And then when we get into the post-agent era where we are now, I would say that the use cases are actually really, really similar pre and post-agents, except the kind of operator changes. So instead of a human being using a system, now we have agentic systems or LLMs that are calling tools and using the system. But realistically, the isolation mechanisms, we're using them for the same types of reasons. All right, so now we can kind of like jump in and define what we're talking about. At its core, isolation is really just about partitioning resources out. So the types of resources can be compute, whether that's CPU and memory. We can talk about users. So in a multi-user type environment, we need Bob can't see Sam's files and Sam shouldn't see Jim's files. So that's one type of resource partitioning. And then the ultimate is going to be at the hardware level. And we'll talk about why this kind of like separate from the compute side in a bit. I think that'll be clear. Before we move on, anybody have any questions? All right, so we'll jump into history for a little bit because I think this frames up nicely why we have these systems. It also kind of illustrates where concepts like containers actually came from. So back in the 1950s, in early computing days, a computer would only run one application at a time. One instance of a program and one runtime for that program. So in the early days of computing, you didn't actually need a lot of isolation or any isolation at all. That starts to change in the late 50s. So in France, the first multi-programming computer was introduced. Multi-programming just means the CPU shares time and can execute two programs at once. So I think I'm probably the oldest person here, but maybe you have a relative that has regaled you with a tale about programming via punch cards and feeding that into a computer. That's a single program computer. And then, that's kind of what old-timey representations of computers that are the size of the room kind of represent. But in the late 50s and 60s, we start to go into a multi-program environment. So the first operating system that could run multiple computers was something called Multics. It was developed in the telecom industry. So think like Ma Bell is kind of at the edge of developing the first multi-program operating system. But it sucks and everybody hates it. So a guy named Ken Thompson, a scientist at Bell, invents Unix. And initially Unix is just a collection of tools. And then he's like, I hate Multics, but I have all these tools for it. I bet I can stitch them all together, create an operating system out of it in no time. So something like 2 weeks, he takes all of his tools that he made from Multics, packages them together, and it becomes Unix. So Unix is quite famous as being one of the first not only multi-programming environments, but multi-user. And then on the opposite side of the country, University of Berkeley is developing something called BSD, which macOS is based on. So that's happening at about the same time. So now all of a sudden you get companies with big adoption of Unix and BSD, which are now multi-user, multi-program environments, and all of a sudden it becomes really important to start isolating things. So on kind of the backs of that, IBM starts to go into virtualization for the mainframe products. So in '72, IBM releases the first thing that we would ever consider a virtual machine. And the entire idea of it is they have this giant mainframe computer, and they want to run 2 copies of the operating system on it at once, give 1 copy to one user and another copy to another user. So 1972, they launch, I think it's called the VM370 to go along with their server 370 product. This is just a big ass mainframe. And then on kind of the backs of this, needing some sort of isolation systems, the traditional mainframe environment has lots of users using this, several programs at the same time. The first real isolation system that gets introduced is called the crew. If you've ever programmed on a Chromebook, this might be like a familiar thing, but a crew is a way to kind of reposition the directory structure of your file drive so that a program can only see this small snapshot of it instead of seeing this entire thing. So that's one of the earliest ways of adding isolation on top of these multi-user systems. And then it's kind of a long time before we have a lot more innovation in this space. So in 2000, 2001, jails start to become a thing. So this is building on top of croups and introducing more types of isolation for processes and resources. So what else is happening in 2000, 2001?
Graduating from high school.
All right, it's also the dot-com boom,
Yeah.
or the dot-com bust, whichever. So like you can see there's like 50 some odd years of like quite slow progress. And then all of a sudden we get a lot of progress on isolation really, really quickly. So in 06, Google creates something that they call process containers or cgroups. So this is very particular for their cloud, but it gets adopted into Linux, merged into Linux upstream and renamed cgroups. Also in 2006, something called KVM is created. It takes advantage of a new update to the x86 instruction sets. We'll talk about that a little bit later. We won't get too deep into it. And then a little bit later in 08, we have the first thing that you would ever consider a container. So the first version of a modern container doesn't actually happen until 2008. It's called LXC. So these are Linux containers. And it's really just combining different types of isolation mechanisms all into one. Docker is actually published by a company called .cloud back in 2013, and they were building on top of LXC, but what they introduced was a build system. So Docker build, buildx, those types of tooling didn't exist until Docker created these. And this is really the explosion of containers in the ecosystem. And it really coincides with the rise of SaaS products as well, and kind of becomes the de facto standard for how we deploy and manage SaaS applications. But the big thing that they did was make building an image and packaging an application really, really easy. So that's the cool innovation that we see from Docker. And then a couple years later, .cloud really decides to index on this containerization solution. They rename themselves Docker, and they release Containerd and then libcontainer to the world as open source. And these are kind of the management layers for containers at large. And we'll kind of see why that's important a little bit. All right, so that's hopefully interesting and hopefully helpful for kind of the base level of how we got to 2026 for isolation system. Does anybody have any questions before we jump into the kind of mechanics of different systems? All right, I'm not paying attention to Zoom at all, so. Oh, I see, okay. All right, so when we talk about isolation systems, we're going to start with individual resources. So these are, again, starting with the croups, kind of like the building blocks for isolation. So the primitives of these, you can see memory and CPU. So these are compute resources. We also have your file system, that's the crew. Processes. So if you've ever used a V8 isolate, it's a process isolation system. So a V8 isolate is part of JavaScript. What it does is spins up a isolated instance of JavaScript that has its own heap. So the heap is a memory construct for things that are kind of allocated on the fly, which is the vast majority of everything in JavaScript. This may sound like a little simple if you've never worked in a language like C, where you have to allocate your own memory, but having a protected memory structure is a relatively new concept in computer science. And then we also have namespaces within the process. So namespaces are probably the thing that is most familiar to application developers. We use the same paradigm basically everywhere in application development. So if you create a user system, so at Flatfile we had a system where we would intake lots and lots of documents from our customers, and then you need a visibility layer on top. So customer A shouldn't be able to see customer B's layer. So we introduce a logical system for isolating those resources. And that's essentially what namespaces are. They say if you're tagged inside this namespace, you can't see things outside of the namespace, you can only see things within your own namespace. So that's kind of the idea. But it's really just this logical abstraction on top of things like file systems and networks. And then finally, the network itself, also a pretty important part of isolation, especially in like a multi-tenant environment. So if you've ever run like web workloads on a like a bare metal server, a lot of times you have multiple applications all running at once. One, you don't want a noisy neighbor effect. Partially that's what things like cgroups and ulimit are protecting you against. But especially if you don't particularly trust all the different services running on your service. So like if you're hosting APIs or applications for other people, you could say that those are untrusted code. If you're going to co-locate them on hardware that you own, you need to segregate the resources so they're not jumping across boundaries. Kind of the way Docker does it, and a canonical way of doing that is typically a bridge type network. But these things are imperfect systems. They're not all completely designed around isolating from attackers. They're mostly isolation systems for how we want software to behave. So things like ulimit and cgroups, any kind of privilege escalation can certainly get around that, and then that can create noisy neighbor effects, being that if you have two applications and you have one without resource limits, if that consumes 100% of the memory on your box, the other application gets starved and something crashes and dies. Files, croots are incredibly simple. So croots are essentially like redefining the entry point of your file system. You do something called a pivot croot and immediately get out of it. Pivot croot is just creating a croot within a croot. So you redefine your own file system, which makes it quite imperfect for actually isolating files. Processes. So V8 isolates is pretty good, as well as namespaces, but they're still easy to get out of. One aspect is that you have a kernel for basically all systems. Kernel, does everybody know what that is? Yeah, it's the set of APIs that work with the hardware. So it's got a lot of functions in it directly. You can access those functions from any namespace. And as it turns out, by accessing kernel functions, you can get out of your namespace. And then networks. So a bridge network is also imperfect. You can take advantage of the loopback, which is localhost networking on a host system, to get around a bridge network. You can also access sockets directly. So a Unix socket is just a file that sits on the directory. So if you have access to the file system, you can figure out how to connect via socket immediately. So resource-based isolation, it's pretty good. There's definite boundaries for each type of isolation, however. All right. Any questions? All right. So we'll move on. So the same set of primitives. If you put a management wrapper around all these primitives, that's a container. So that is really all a container is. I think the first time I used Docker was probably like 2015, 2016, something like that, and I thought it was magic, and I had no fucking idea how it worked. But as it turns out, it's not that complicated. It takes these isolation primitives and wraps it in a daemon and a management layer, and that's essentially what we consider to be a container, or the modern equivalent of a container. All right, so that container ecosystem has given us a lot of big benefits. Images and distribution being probably the biggest benefit to this ecosystem. Scalability is also up there. So for a well-understood application, it's quite easy to take a control plane like Kubernetes, apply it here, and get a lot of benefits out of both the isolation system here to get good density out of the underlying hardware. And then security. Honestly, containers are good enough for most things. So there are ways of escaping it. You have to be pretty purposeful, which means you'll have to be running basically untrusted code or untrusted commands in order to escape that. So that's the part that gets kind of iffy in the agent era. I would say that my personal thoughts on isolation are you use something that's appropriate for what you're doing. If you're using a off-the-shelf agent harness like Cloud Code, that ships with its own sandboxing mechanism. So when we say sandbox, that's really just like some isolation system. The Cloud Code sandbox is actually a deprecated Apple API called sandbox exec. It's essentially a namespace. So it's the BSD equivalent of namespacing, which Cloud Code takes advantage of to not totally fuck up your system. And then containers offer kind of another abstraction, more isolation, and it's honestly pretty good. If you need to run maybe a system of agents or sub-agents, Docker containers work really well for something where you kind of understand the bounds of. So it's not always great for, I would say applications in which users are supplying maybe the agent harness or other things. But certainly if you understand the bounds of your application, containers work great. Right. And then containers also have their own complexity. So because it's made out of a group of primitives, there has to be a layer to manage that. So what we're looking at here is kind of an illustration of the Kubernetes control plane. So if you guys have used Kube before, it's a control plane that sits on top of a collection of hardware. The hardware is the physical server called the node. So you can have a collection of nodes. The control plane manages workloads across those. You have the management layer, you have the node, you have the pod, you have the container, and then you actually have your isolation mechanisms down at the operating system level. So you actually have to drill down several layers before you actually get to the isolation. It makes for a fair amount of complexity for running workloads. So if you're running a giant container fleet because you're Google and you have 10,000 servers to run your apps on, it's great. If you're running just a small handful of applications, Kubernetes is generally overkill. I would say in my experience, 90% of shops that are running Kubernetes have no business running Kubernetes. And most of it's really just due to the complexity that you kind of see here. All right, so we're going to move on to virtual machines. So virtual machines, whereas containers and those individual process isolation, those are highly related. Virtual machines are kind of a world by themselves. So they are split into two different types. So a type 2 hypervisor is going to be like the virtualization that runs locally on your MacBook. It's great, it's fast, it does sit on top of the operating system in something we call user space. So user space has its own set of privileges and its own problems. Typically, these are going to be a little bit slower and more complex than a type 1 hypervisor. So a type 1 hypervisor is going to be like KVM or Microsoft's Hyper-V, and it's going to directly interact with the hardware itself. So it sits kind of below the operating system. You get hardware, kernel, hypervisor, and then operating system. So it's more deeply ingrained. It gets you really tight isolation, like you can see here. So this is specific to kernel virtual machines, which are kind of the, I would say like the de facto standard in 2026 for how we operate VMs. So KVM is a set of APIs that are included within the kernel itself. So they were created in 2006 by an Israeli company, and they were actually created for high availability. So this company had these, had their hardware, these servers, running a monolith for getting like remote desktops on Windows machines. That was their application sitting on top of a server. They needed to run multiple copies of this on every single physical server. It was kind of a quirk where AMD and Intel released like a new update to the instruction set that allowed KVM to be really, really fast. Before this, you had to launch a virtual machines with the same privileges as the host, which is very, very dangerous. If a VM has the ability to do anything the host does, then that kind of defeats the purpose of a VM. Or you could go the opposite, where it's extremely stripped down and basically loses a lot of capabilities, especially with devices. So Intel, AMD got together, they released a new privilege ring, and KVM takes advantage of that privilege ring to basically spin up guest kernels super, super quick. But the key thing on this diagram is really that programs and applications, they're running in user space on top of the kernel. When you get a boot a VM in KVM, it's going to create an entire guest kernel, and then the user space sits on top of that. So the user space is completely segregated in a virtual machine, which makes the bounds of that isolation extremely tight. Rather than having a lot of logical processes, which are things like cgroups and namespaces to provide isolation, this is essentially a walled garden, and nothing can transit between user space. So this really creates like the tightest level of isolation that we can get. Still though, so I mentioned before about the permission rings that KVM takes advantage of. The reason it's fast is because previous VMs had to kind of build on top of the host operating system in order to give you anything useful, while the KVM is going to interact directly on the hardware level, which makes it really fast. And then as an example of how this is kind of being taken advantage of right at this moment in time, the agent computer has kind of emerged as one of the bigger patterns for hosting agents at scale. Really that relies on the host system having two pieces of the virtual machine, a root file system and then a kernel. So the kernel is the device APIs. The root file system is what contains essentially the operating system, the program, application, all the tools for it, hosted within that root. Then within that guest, you're going to have your agent harness and all the tools. That gives you a lot of benefits. The agent can kind of manage its own environment in a safe manner because it's clearly segregated within its own user space. So, if you want to give your agent sudo, this is probably the safest way to actually accomplish that and provide kind of high enough density on the metal that it's hosting. Okay. And then, does anybody have any questions on the agent? I don't know. I know you've built agents before. Okay. So a couple additional things that are kind of related to the isolation thing, but pretty specifically with how infrastructure works today. So the big hyperscalers are highly optimized for container workloads. One aspect of that is a container workload is expected to be very ephemeral and stateless. So that means that it's not saving a bunch of individual files to disk. Each container could be killed and restarted, and you don't lose anything. And that's really what an AWS or Azure or GCP is really designed for. So it's very ephemeral, stateless workloads. Another aspect of that is that if you walk into a data center managed by AWS, the compute memory is likely going to be in one rack. The storage is going to be in another rack, likely in a different building. So you can have miles separating your disk from your actual compute. This works just fine in a container environment for most SaaS applications, because those applications are not hitting the disk every time. Agents are not like that. Agents really like to hit the disk. If you think about memory files are often stored in disk or like a small database like SQLite. SQLite is just a file on a disk. We also give it tools like Bash. Bash tools are primarily file system-based tools. So agents are going to hit the disk multiple times on every turn. The problem is you're going to definitely introduce latency if you have to go to a separate building. SpeedOlite is fast, but you can't overcome physics completely. So if you think about a bare metal machine, which bare metal and virtual machines kind of go hand in hand. Even the compute that Amazon gives you is a bare metal machine with a hypervisor with a VM running on it, so it's already got these multiple abstraction layers. But the bare metal directly is really good for that type of stateful interactions where the agent is going to disk constantly, and it kind of gets around this like data center architecture issue. All right. Cool. That is the ball game here. I have a bunch of resources here, so if anybody's interested, I can send you this presentation, and then you can cruise at your will. But yeah, do you have any questions?
So, if you're running plot code, that's obviously, we're talking agent there. I mean, it's not a VM.
No.
It's its own world, so to speak. Kind of comes from that thought process. So then, you say pseudo. Obviously, you probably shouldn't give your plot code pseudo access, but obviously.
Yeah, the reality on the ground is most people let Cloud Code do whatever they want, whatever it wants. Yeah, so it does use an isolation system that's based on namespacing. So namespacing is like a logical isolation system. It's imperfect, you can escape it.
Because one of the things I see with agents now with skills.md markdown files, with people are downloading skills from skills.sh, 30, 40 skills at a time, you're probably not reading through the skill to figure out everything it's doing, and now we can start hiding prompts, do a prompt injection, and now say, oh, you have pseudo access, go delete the root file system. Because you didn't read the skill that you just downloaded, hoping that it was on that. So that's it. I can get it.
Yeah, yeah. I mean, I would say again, like you should use the isolation system that is like really warranted. If you're, like taking a lot of things that you can't really trust and running them directly on your host, yeah, you might want a tighter execution environment than just namespacing. I think for most people that are manually driving a Claude session, like the namespacing works pretty well. If you're driving multiple agents and using like a work tree type thing, well, that's 2 levels of isolation because you get a real lightweight file isolation plus your namespace isolation. That's okay for just running this stuff on your own hardware. If you're instead, maybe you got an agent that's prompted via Slack integration or something like that, which is be multi-user, any person in your Slack group or whatnot has access to that and can submit prompts. That's kind of somewhere where you probably do want another abstraction on top of that. So maybe if it's all people in your company, it's got a limited set of tools, then a container works great for that. If you're selling that as a service, so you're like Devon AI, something like that, you're going to want something more like a virtual machine.
And just that's nothing that I kind of ever considered. I'm smart enough to know sudo rfrm force is not a good thing, but again, with people now just downloading skills for 100 tools they're using, I did the same thing. I set a skills directory and hey, I'm using React, I'm using Vercel, I'm using Next. Scrap all the skills. I'm not reading through 70 files they drop in there. Sure, if you're
Auto mode on.
auto mode on, God mode, and just do it. I'll come back in 2 hours and have a smoking computer at that point. Cool.
You're going to have a operating system built for agents to code in, and have an agent like trained or model trained for that operating system. You won't break out of any bounds or do any squirrely stuff. Like I feel like
Yeah, I mean, I think training is a pretty imperfect way of controlling an agent, for sure. I think at scale, the virtual machine is just like a great implementation for it. Especially now, like KVM, which tools like Firecracker built on top of, they're performant enough that you can create these environments and fork them and launch them at scale. So then you're kind of like managing artifacts that the agent creates at that point, but the bounds of that agent are still pretty locked down. I think at the moment, agents are really good at standard Linux behavior. They're quite well trained on that. I think I did have a conversation about like what a language for an agent would probably look like, and I think it would look more like a state machine, and that might actually be like a better implementation for like the agent loop if it is really just entering into this some sort of state machine to kind of manage tools and processes. Like a standard Linux shell seems to work pretty well. I think.
Well, thank you very much for signing up. Thank you for the talk, and hope to hear from you again.
Yeah, for sure, man.